All right, this video is going to cover collision. Going to be a bit of a doozy, but we'll see how it goes. So once again, the game object inherits from the collidable class, so that gives it certain properties. And the scene has a collision manager, so that's how we do all this stuff. I'm going to walk through this like from the perspective of a game object that wants to set up collision. So the first thing you would do, well, the order here isn't super important, but would be setting the collidable group. So this goes through the collidable, and then it requests that for the collision manager for this particular scene, I want to have register for a particular collidable group. So basically, the collision manager has a group, which is a vector of collidable groups. Collidable groups are basically just a way to mark different user-defined game objects in different groups. So for instance, there will be a tank group and an enemy tank group and a Lego group, you know, for all the different types of things that you want to register, but we don't know what types the user will have, so this is the way that the engine can deal with it. So we have this list of collidable groups. When you sorry, I forgot what I'm losing my train of thought. So when you set this collidable group, you basically set the ID for this particular collidable will be the ID for this particular type. So in the collision manager, get type ID, you have this static variable that's basically assigning these integers to these different types, and you're going to set that group. Which will create a new variable group if it doesn't already have one. So yeah, so if the index for that particular type hasn't already been created, then you're just going to create a new one. So anyway, now you have this collidable group for, you know, if we're registering a tank, we have a collidable group for the tank that the engine can recognize. The next thing you need to do is in your scene, set up these collision pairs between two different types. So in this case, the tank is a collidable group. We can assume that the obstacle is a collidable group, and we want to set up this collision pair. So back to the collision manager, setting up a collision pair. You are getting the two different groups, getting the pointers to those based on the group collection that you have in the collision manager. You're creating a collision dispatch that is a templatized class that is specific to these two types. So basically the job of the collision dispatch is to know the two types, like very specific two types. Okay, there's going to be one of these for a tank and an obstacle. It'll have its own class, so it knows which types there are. So then when you detect the collision, you can actually call on these two objects the corresponding collision methods that the user is going to implement. So that's how you can actually call the right things, is by creating this collision dispatch. So when you set the collision pair, you do that, and then you also create a new test pair command with both of these types and with a pointer to that new dispatch. So basically the collision manager is going to have a list of collision commands, test commands, and in process collisions, which is called every single frame via the scene's update, you're going to execute every single one of those pair commands. So every pair of objects, or if you have you can also register to watch for a collision between two objects of the same type, but you're going to test if those things are actually colliding every single frame. So what does this class look like? We'll just focus on the pair command. Pair command has the pointers to the two different collidable groups and the dispatch. Every single frame you call execute on this pair command if this pair has been, you know, the user has said that to watch out for this pair. It loops through every single object. It does pairwise comparison between every single object in the first collection and the second collection. So it's looping through all the tanks and all the obstacles to see if any of them collide. So it's not super smart at this point, but it works for now. Gets their bounding spheres, which I'll talk about in a second, does their intersection, and then if they do intersect, let's just say we magically know that it does, it's going to process the callbacks, which once again goes through the collision dispatch, process callbacks, and calls collision on both of those things. So for the tank, that would be collision with an obstacle, which stops the movement, and then obstacle collision with a tank doesn't do anything. It's just an empty class, or an empty method. But that's how that's supposed to work. In terms of how do you actually detect these collisions, that's where the bounding spheres come in. So basically we're going to have more collision volumes coming up, but this is the base class. It doesn't really do much right now. Right now we just have bounding spheres. A bounding sphere is like a theoretical thing a theoretical shape. I mean, it's real, but and it has a center and a radius, and based on the model, the location of the model that you are trying to detect collision for, it will update the data of this bounding sphere accordingly. And yeah, so basically every single collidable has a bounding sphere associated with it. When you are setting up collision, you have to say, hey, I want to set my collider model to be this model, so the graphics object's a model. And what that does is it gives the collidable a pointer to that model so that later, during your update loop, every single time your object moves, you need to update where the bounding sphere is as well. So you have to call, give me a moment to find it, update collision data. So what update collision data does is it updates where your bounding sphere is so you can detect collisions correctly. So it says bounding sphere compute data, and that compute data says, okay, the model that we have, which was saved into the collidable, I need to get its center, multiply by whatever world matrix that the object has been transformed by, do whatever scaling that you need to do, and update the radius. So now this bounding sphere has the correct center and radius to match the model that we care about. So that means that when you're doing your pair command, you can get both of these bounding spheres for each of these objects that you're comparing and test if they intersect. So this is where the math tools comes in. Gemini Math Tools is just a class. It's a static class, and the purpose of it is just to hold static math tests. I'm losing the vocabulary for it, but it should just be a thing where you can pump in numbers and get back results. So this just checks if two bounding spheres intersect, and it returns true or false based on that. So there's the math for that. In your pair command, if that's true, then you do the process callbacks via the dispatcher. Yeah, so that is how you actually do the testing through that, like updating the collision data, blah, blah, blah. The last thing is the visualizer. I'm actually going to uncomment these. So basically, you might want to actually look at where these bounding spheres are and see if things are interacting. So that's where the visualizer comes in. It is a singleton class, and every single frame, visualize all is called, and it goes through all of its visualize commands, executes them, or cycles them. So if you want to visualize something, like in this pair command, I say visualizer submit B-sphere visualization. I tell the B-sphere that I want, and I say the color. When you submit a request to visualize something, it goes through, basically the visualizer gathers all of the visualization commands during the frame, and then it executes them all. So you get, I have a command pool for the different commands, and then a B-sphere command in particular. So if you want a B-sphere visualization, you get the B-sphere from the command pool, initialize it with the center and radius and color that you want for this particular visualization, and then you push that back into the list of commands. So then when you're looping through them all and you execute the B-sphere command, you have saved all this information, and then you do show B-sphered with all of this information, and show B-sphere is here, and you find the transform matrix. Okay, hold on, give me 1 second. When you create the visualizer, you load in this one sphere. So basically every single thing that you're visualizing is using the same sphere, the same model, and then you just find the world matrix that you need to move it to represent this particular B-sphere, and then you render it, which is right here, where you set the color, set the world, and render it. Yeah, so long story short, I think this should work if I run it. So everything has the corresponding bounding spheres, and my stuff is scaled all kinds of crazy, so you can definitely see that the scaling works. If I collide with something, I stop, excuse me, and you can see things turning red when I'm colliding with them. So when I collide with these guys, they turn red. excuse me. So yeah, collision's working, obviously, because my game processes collision. And yeah, that was a very long explanation, but hopefully I covered everything. This is gonna wrap up this video.